Hi everyone, this is Kaiming. Today we're going to talk about tricks to reduce overfitting in deep learning. I will introduce a few common techniques and try to give you a very big picture in a limited time. So without further ado, let's get started. So before we introduce tricks to reduce overfitting, we need to first understand what overfitting is. And that brings us to the bias variance trade-off. A large bias means that your machine learning model deviates from the true value on average, and a large variance means that your model fluctuates too much given small changes in your inputs. To the right, we have an illustration of bias versus variance. Bias measures on average how far you are from your target. Variance measures how much you vary at each shot. In deep learning, we need to find the right balance between bias and variance. The reason is that on the training data, the bias decreases with larger model capacity. However, on the other hand, variance grows with increasing model capacity, since now it has more parameters to remember every data point you have. Good deep learning models should have low bias and variance at the same time, but this is often hard to achieve. Overfitting is the case where we have high variance and low bias on the training data. Remember that we want our model to perform on new data, while overfitting means poor generalization on new data. Now, how do we actually reduce overfitting? Here are a few commonly used techniques in deep learning. The first one is L1 L2 regularization. Since overfitting happens when large model capacity hinders its ability to generalize, we can punish the model for having too many parameters. That's exactly what L1 L2 regularization does. This trick adds a L1 or L2 norm term into the loss function, which the model tries to minimize. Therefore, L1 L2 regularization helps reduce overfitting by decreasing the norm of model weights, and in terms of L1 regularization, by making them sparse. The next one is about dropout and drop block. Dropout deactivates neurons in networks by setting their activations to 0. What dropout does is to implicitly impose data annotation, and also to force the model not to rely on any certain pixels too much, thus reducing overfitting. Since neighboring pixels are often highly correlated, drop block proposes to drop an entire block in the image or the feature map, just like the rightmost image does. Another simple trick to reduce overfitting is what we call early stopping. As the training goes on, the model reduces bias and increases variance on the training data, and loses its ability to generalize. What early stopping does is to simply stop the training procedure when the performance on the validation set no longer improves. So the next one is what we call mix-up, which is a little bit tricky. So deep learning applies the idea called empirical risk minimization, which basically means to minimize the risk or the loss on your training data. This might cause problem because you may want to generalize to distributions which your training data doesn't cover, just like the blank area between the green circle and the orange circle around here. So what mix-up does is that it generates new training data by linearly combining two data samples, like what the pseudocode here does. So with new training data, mix-up enables training on convex combination of training data, just like this blurred blue area in this right image, and therefore it can increase the generalization ability of your deep learning model. So the last technique of today is called label smoothing. This idea is inspired by the observation that the minimum of cross-entropy loss is unachievable for finite logits, which would encourage deep learning models to overfit to data and become too confident. So this is what label smoothing does. Suppose we are in a binary classification case. Instead of using the true labels of 0 and 1, We use an epsilon to set zeros to epsilon and ones to 1 minus epsilon. This trick makes the minimum of cross-entropy reachable and encourage the model to be less confident, thus is able to reduce overfitting. Okay, that's it for today. You can look for these papers if you want to find out more about the details. I hope that these tricks are helpful in reducing overfitting of your model. Thanks for watching.